We now apply Gauss's law to a few simple cases, and the first one is, if we say that if we have a few discrete point charges, then what happens? So it's application of Gauss's law. So if we have a point charge here, which is, let's say, a positive Q1, and we have a negative charge here, which is a negative Q2, and let's suppose there's a third charge here, which might be a positive Q3, and we have an area here, which is our A1, and we have an area here, a volume, a closed volume A, having an area A1, and a closed volume having an area A2. So what is the flux through A1? That is going to be 0, because Q in is 0. There's no charge inside. This charge and these charges will have no effect, will have no net flux on A1. There will be flux coming in, there will be flux going out, so net flux is 0, and therefore phi is 0. Now in this one, the net flux is going to be Q in over epsilon naught, and Q in is the sum of these two charges, so it's going to be Q1, this being negative, Q2 over epsilon naught. Now if Q2 is bigger than Q1, there will be a net negative flux, and if Q1 is bigger, there will be a net positive flux. So we'll just plug in the numbers over here, divide by epsilon naught, and we get the flux. Now of more, let's say, interest is that if it's not a point source, not a point charge, but a volume charge, so we'll take the case where we have a sphere a solid sphere, and it has a total charge of Q coulombs, and this charge is uniformly distributed in the entire volume of that charge. Okay, so in the entire volume we have a very uniformly charged distribution. The radius is taken as A, and we want to find the electric field, let's say over here. This is our point P. The question is, what is the electric field at P? Now, some points which are closer to P will have a greater effect on the electric field here. Those points which are further away will have a smaller effect. Those points which are here will push electric field this way. Those points which are here will try to push the electric field this way. So what is the net direction of the electric field, and what is the net value of the electric field? So the charges that are closer will have 1 over r square, so they will have a strong effect. Those which are further away would be weaker. So in order to solve this, we use Gauss's equation, and that is that the flux is Q in over epsilon naught, and that is the integral of E dot dA, and that's the E that we want to find. Epsilon naught is easy, but we need to find the other things. So the procedure is that the first thing we do is we make what we call a Gaussian surface. This is an imaginary surface which is spherical in this case, because this is spherical, and it's concentric with this sphere. So we make a Gaussian sphere or surface which is also a sphere, and it's at some distance from here, and doesn't really matter what the distance is, but let's say that it's at a distance r, and this is the distance r from here. The total charge is q. Now in order to use this equation, we must have a great deal of symmetry. If we don't have symmetry in the problem, then we cannot use Gauss's law. So here we have created symmetry because this is spherical and this is also spherical, and both spheres are concentric, so they have the same center. And the charge is uniformly distributed everywhere inside, so that also creates symmetry. Now, because of this symmetry, what we can assume is that the electric field at any point has to be pointing radially outwards, coming straight from the center. Because if the electric field were not radial, suppose the electric field were like that, at a point, well, the other points from where it would intersect, and that can't happen. So the electric field everywhere has to be pointing radially outwards along this entire Gaussian surface. So the electric field is going to be pointing this way at the point P. Now, the area at every point is also pointing straight outwards. So at every point, the area is also pointing straight out. So here, the area is also pointing straight out. And so what we have is that the area and the electric field are parallel, or the direction of the area is parallel to the direction of the electric field, which means that E dot dA at every point is E dA cos theta, and theta at every point is 0, and so it's E dA. And we can replace the vectors with simply numbers. And so the flux, which is Q in over epsilon naught, becomes the integral of E dA. Now we'd like to find these terms. So what's Q in? By definition, Q in is the charge that's inside the Gaussian surface, and that is equal to Q. So Q in is simply our total charge. The electric field at, well, that's what we're looking for. But we know that the electric field is pointing outwards, and also because of symmetry, the electric field has to have the same magnitude everywhere. So the magnitude of the electric field has to be the same over the entire Gaussian surface because of symmetry. And because it's the same, we can take it outside. So we'll replace the Q in with capital Q, and we will take out the E, and we have an integral of dA. So we need to integrate dA over the Gaussian surface. And the integral of the area over the Gaussian surface, this is simply EA over the Gaussian surface, and the area over the Gaussian surface is 4 pi r square, where r is the radius of the Gaussian surface. And so we can write Q over epsilon naught is E times 4 pi r square, which yields that the electric field is Q over 4 pi epsilon naught r square. I brought it down and wrote it like this. And now we know again that K, 4 pi K is 1 over epsilon naught, or K is 1 over 4 pi epsilon naught. So we replace this with K, and therefore the electric field becomes equal to K, this whole thing is K, 1 over this is K, Q over r square. That becomes the magnitude of the electric field, and the direction is radially outwards. Now this is the same equation E for a point charge. is simply kq over r square, and this is the same thing, which means that this distributed charge, where the charge is over this whole spherical surface, behaves as if the charge were concentrated in the center, so far as the electric field outside it is concerned. And that is the same as for gravity. So if we have the Earth and we want to find the, let's say, the orbital period of a satellite that's going around it, then we assume that we just say that the satellite is a distance r from the center of the Earth, and we say that the force on the satellite is simply g, mass of the Earth, m of the satellite, over r square, and we assume that, which assumes that the entire mass of the Earth is concentrated at the center. So the same thing applies for an electric charge. We now solve a problem that's somewhat slightly more complex than the previous one, but still the same thing, and that is, let's suppose that we have, let's use this, if we have a solid sphere with a uniform charge distribution, so same condition as before, solid sphere, and the total charge is q, and it's uniformly distributed. In the entire volume. But now the question is, what is the electric field inside it? Somewhere here. So let's just make another sphere. And let's say this is concentric with the first, and what's the electric field here? And we'll make a Gaussian surface over here. Well, this should be concentric. So that's our point P. The question is, what is the electric field at the point P? That's the center of the sphere. So our Gaussian surface is now inside our sphere. And so we have the flux is q in over epsilon naught equals the integral of E dot dA, where we will apply this over the Gaussian surface. Now, what we need to find here is what is q in. Q in is going to be the charge in this region. This is q in. And q is the charge in the entire sphere. The whole thing is q. So we can see that q in, if the charge is uniformly distributed, is going to be equal to the total charge times the volume of this Gaussian volume over the total volume, which is going to be q. Now the volume of a sphere is 4 by 3 pi r cubed, so it's 4 by 3 pi. Now we need to set up some notation. So we say that this is A and this is R. So it's 4 by 3 pi r cubed over 4 by 3 pi a cubed. Now the 4 by 3's will cancel, and that's going to be q r cubed over a cubed, and that will be our charge q in. So now we can replace q in with this. Another way of doing this is to say that we have rho, which is the volumetric charge density, and that is q over the total volume. So this part is the volumetric charge density, and then q in is going to be the volumetric charge density times the V in, which will give us the same thing. So now we can replace the q in with this thing. That's q in. So that goes in here. Epsilon we know, Now we need to look at some symmetries. So again, because of symmetry, the charge distribution is uniform, the two spheres are concentric, and therefore the direction of the electric field must be parallel to the direction of the area at every single point. The electric field has to be pointing this way. So, and the area is also pointing this way. So both the E and the A must be parallel. Secondly, the magnitude of E must be the same over the entire surface. We can't have a bigger E here and a smaller E here, because the distribution of charge is uniform and this is a sphere. So E at R is constant. The magnitude is constant. Now because they are parallel, so E dot dA becomes E dA cos theta, and theta is 0, becomes E dA cosine 0, becomes E dA. And so we no need to worry about the angles. And because E is constant, we can take it out. So this becomes E dA. And so we will replace this whole thing, which is here, with E dA. And the Q in we replace with this. And we get the flux is Q in, which is Q R cubed over A cubed. That's Q in over epsilon naught equals E integral dA. And we need to do the integration over the Gaussian surface. So the integration of the area is simply the surface of this green sphere, and that is E 4 pi r square. And so our E, we can write the E here, is going to be Q r cubed over A cubed epsilon naught and divided by 4 pi r square. And we can cancel out the r square with two of these, and we're left with 1 r, and therefore E equals Q r over 4 pi epsilon naught, and 1 over 4 pi epsilon naught is K. So this thing becomes a K and A cubed. And so our electric field at the point P is given by K Q R over A cubed. Now what happens as R gets smaller or bigger? So we can see the trend. Let's suppose that this is our sphere, and that's the center of the sphere. So let's draw a line here. So the electric field when R is 0, this distance is A. When R is 0, this whole thing is 0. So the electric field right in the middle, this is the E, electric field is going to be 0. Now as R increases, and we are still inside it, so up to here this is A, we're still inside it. As R increases, the electric field increases, so it's going to keep getting bigger and reach a maximum value over here. Now what happens outside is what we had earlier, that E equals KQ over R square. That's outside. And so as R increases, this thing gets smaller, so it's going to go according to 1 over R square. So that is going to be KQ over R square, and this part is going to be KQR over A cubed. So the electric field is maximum on the surface, it's 0 at the center, and it drops off as you go away. The same thing also applies to gravity, the force of gravity. So if this is the Earth, and if you dig a deep hole and go into the Earth and go over here, what will be your weight? So on the surface everywhere the weight is mg, and as you go away from the surface the weight gets smaller because g gets smaller. But what happens as you go inside? So if this distance is r and the radius of the Earth is re, then as we go inside the weight will become smaller because the gravitational force gets smaller, and it follows exactly the same kind of equation that we have over here. Well, this is for charge, but it's a similar equation. So as we go into the Earth, our weight gets smaller because the force of gravity gets smaller, and as we go away from the Earth, again it gets smaller, and the value of g is the largest on the surface of the Earth. So when we reach right in the middle of the Earth, we would become weightless, right at the center of the Earth, just as the electric field will become zero and the center of a uniformly charged sphere. Also, the same thing applies here, that the weight over here would depend on the mass of this part of the Earth. So whatever is the mass of this part of the Earth, we would use that and assume that, well, this rest of the mass has no effect. That's because this part of the mass is pulling outwards, this part of the mass is pulling downwards, and this is further away, it's more but further away, and they exactly cancel out, just as what happens here, that for a point that's here, whatever is the charge outside is of no effect. The electric field is only due to the charge inside, and here the gravitational force is only due to the mass that's inside that particular sphere.